So welcome back to the afternoon session. Start by Chen.
So good afternoon, everyone. My name is Chen Li, and I am from Erasmus University, Rotterdam. Today I'm going to present a project on signal perception and belief updating. It's a joint work with UK Edouard Bayon, who are both from Erasmus, and Emmanuel Kemo, who is one of the organizers of this workshop. So you don't see him yet. But well, later if you have questions, then I will ask him to answer. So in the literature of belief updating, so often we find that people deviate from Bayesian updating, and they exhibit all kinds of biases. So here I give you some examples, but if you look into the literature, you can extend this list extensively. But most of these studies, they are rather qualitative in the sense that it can qualify, it can say, oh, this person exhibits this bias if you can see a certain pattern in his, let's say, reported judgments, behavior, choices, etc. And what is not so much known is the quantitative part. So one of the aims of this project is to answer the question, how much is the deviation? And we do that by providing quantitative measures of biases. And having such quantitative measures can be very important. For instance, it can help you evaluate the effectiveness of policy. We can also use them to give advice to people for them to incorporate such biases when they do things. For instance, in one Chinese folk wisdom says, if you have something important to say, repeat it 3 times. So why is that? At the end of the presentation, you will see that actually our empirical finding had some empirical evidence supporting this claim. So we found that on average, when people receive information, they tend to miss 2/3 of the information. So then if you repeat 3 times, you kind of think that at least once they get it. So to provide such a quantitative measure, we first propose an economic model that is tractable. So its parameters also have meaningful empirical interpretations. And also, it can be observable from people's choices. So it's consistent with the real revealed preference paradigm. And on the psychological part, as I said, we provide quantitative measures of biases, and we try to capture a spectrum of different biases. So we start from 2 main biases, namely confirmatory bias and conservatism bias. So confirmatory bias refers to people's tendency to misread contradicting evidence as confirming their prior hypothesis. So if I think that I'm smart, and then I failed an exam, and then I think it's really bad luck. So this can be one example of confirming my prior about my high intelligence, for instance. And conservatism bias captures a different dimension. So it captures people's tendency of insufficiently incorporating new information when they update their beliefs. So I mentioned on average, people tend to miss 2/3 of the information that they get. So we will start from 2 indices that capture these 2 main biases. But we don't restrict these biases to only capture the certain direction that I mentioned a moment ago. Because in theory, we let the indices to capture both, let's say, confirmatory, but it also can capture the opposite of confirmatory bias. So in theory, we allow it to take both, let's say, positive and negative values. And then empirically, we test which is the prominent prevailing pattern. And on top of that, we could also study related phenomena, so phenomena that are related to these two biases. For instance, there is this primacy and recency effect, which means people place more weight to the signals that they receive in the beginning and in the end. The primacy effect would then predict that the conservatism bias index would decrease because then they place more weight to the initial signal. Captures his prior.
What about a non-Bayesian using a non-beta prior?
So that is our setup can also be applied to that situation as long as the decision maker's belief only depends on the type of signals that he perceives. So it does not really require it to be a beta distribution. So I gave an example so that it's easier to follow. So what happens to this non-Bayesian updater after receiving the same set of signals? So he does not need to, so his posterior does not need to reflect all the signals that he received. So for now, we denote it by alpha and beta. And in general, it does not have to be, so alpha does not have to be A, and beta does not have to be B. And we call alpha the perceived success. So what this subject perceived in when he received these signals. And beta, the perceived number of failure. And later we are going to look at how alpha and beta deviate from A and B and construct our indices of biases based on the differences.
The posterior is still assumed to be additive?
It's still assumed to be a beta distribution, yes.
The person is non-Bayesian in updating, but he remains Bayesian when above.
Right. So the Bayesian deviation from the Bayesian updating really comes from how he So it comes from the way he processed the signals. But after that, then we assume that, wow. So after that, we assume that they still apply the Bayesian updating. Yes, that's the assumption we make. Yes?
Thomas Palfrey and Stephanie Wang, they have this experiment how to update values and goodies.
Yes.
Overreact and underreact.
So in their study, I don't know the details, but I think their study is more a reduced form. So they would look at people's beliefs and behaviors, and then say, if this person has so and so biases, then you would expect direction of their certain pattern of their behavior. So they don't give a direct quantifiable measure of how big the biases are.
So it's over-interactive. It means you multiply by any good news, the number of good news, you multiply by a number larger than 1. So
Any good news you multiply by a number larger than 1. So it's possible. So you are saying basically alpha can be bigger than A, right? So our model also allows for that. So you will see later. Sorry?
and the relationship is linear.
Is linear. I think it's also linear in our case. Yes. And then we introduce, so eta is the sum of alpha and beta. So it's simply the total number of perceived signals. And I said we are going to use the differences between A and alpha, B and beta to define our indices that capture deviations.
It's a good question, picking up on Peter's question about
Yes.
additivity. Would one way to do that is we have a non-normalized mixed distribution as your prior and posterior? People way to parameterize so that they allow non-additivity.
So I guess then is probably possible, but then I think the interpretations of the parameters will be less clear, and also in terms of tractability, it may sacrifice a little bit. Yes, yes. So now we start with the confirmatory bias index. So we follow what Rabin and Strack proposed in their paper to model confirmatory bias as a probability, QC, of misreading opposite signals as confirming. So how would that be reflected in the number of perceived signals? So let's consider a situation where in your prior you think successes are more likely than failures. So alpha 0 is greater than beta 0. And then after receiving A successes and B failures, all the A successes will be perceived as successes, and part of the failures would also be perceived as successes. And how much of these failures are misperceived as successes is then captured by this confirmatory bias index. And correspondingly, you are going to perceive what is left as failures. And similarly, when you have a case when you think failures are more likely, so you apply the same logic, and then you can get a new set, you can derive the perceived failures and perceived successes. So far we talked about when QC is the number between 0 and 1, so then it can be nicely interpreted as a probability. But if you look at real data, then often this Q can be any number if you only look at the data and the formula. So we don't want to put any constraint on the number on the values that the indices could take, starting from the theory part. So we would also like to give some interpretations of different ranges of values to the indices. So in this case, so if QC is greater than 0, that means you misread not only all the failures that you receive in a sample, you do it even more. So you even may go back into your prior in the hypothetical sample and recode some of the failures from your memory. So we just consider this as an extreme case of confirmatory bias. So then it still can capture in the intuitive sense people's tendency to misread failures as successes. And now, how do we consider the opposite direction of confirmatory bias? So there has been empirical studies that also found people are not always confirming their prior hypothesis. So what we do, we also consider this confirmatory bias. So we call it Q of D. So D stands for disconfirmatory bias. And it's the opposite direction. So you misread confirming signals as contradicting. So exactly the opposite of confirmatory bias. And how does this work? When your prior hypothesis is that successes are more likely than failures, then you actually misread some of the successes as failures and only read the remaining successes as successes. And the other case is similar. And again, when it is greater than 1, it's an extreme case of disconfirmatory bias. So now we have looked at confirmatory bias and disconfirmatory bias separately. But ideally, they are actually the same. So QD is more like the negative part of QC, but with some rescaling with respect to A and B. So I will not tell you the details. But here, so in the end, we actually combine QC and QD into one index. So when does Q take the value of QC? So there are two situations. When you think successes are more likely, and then you actually perceive, so you perceive, I think there is maybe a typo. So the intuition is that when you think it's more likely to have a success, then you actually perceive more successes than when there actually are. And when you think it's more likely to have failures, you perceive more failures than there actually were. And when it's not these two cases, then you probably were disconfirming your prior, and then we take the negative part of the QD. So for this index, if you are Bayesian, then this index is 0. If it's positive, it corresponds to confirmatory bias, and negative corresponds to disconfirmatory bias. Good. Next, we look at the index of conservatism. So conservatism refers to people's tendency to place too much weight to their prior and hence do not incorporate new information sufficiently. And we model it through a probability of missing signals. So in general, so we model it through the probability, a probability P, so that the total number of signals that you perceive, eta, which is alpha plus beta, is only a proportion of the total actual signals. And we do not, for this bias, we do not differentiate between successes and failures. So far, I'm talking about conservatism and ignoring confirmatory bias, but afterwards, I'm going to combine these two. So then we will have a combined model which accounts for both confirmatory and conservatism bias.
Another way to characterize conservatism from a Bayesian perspective as not so much putting the right weight on the prior, but having a degenerate prior, a prior that's really tight. For example, if it gives 0 weight to where the data is, it ain't going to do a damn thing. That's very conservative. That's a standard Bayesian problem in terms of making sure you've got something that's diffused.
But why would you,
Well, I'm just saying conservatism is you don't update sufficiently.
Right.
That might be an artifact of having an ill-formed prior that is either degenerate or gives 0 weight to an area where the events are occurring.
But in the case that you are mentioning, then, so if we don't judge whether whether having a certain prior is rational or not, so then if you just happen to have degenerate prior, and then you still apply Bayesian updating. So you may not be biased, but you don't.
But all I'm saying is there's a label here called conservatism. I think I understand what that is. There seems to be there are several observationally identical Bayesian ways to characterize that. That's all I'm saying. But this is interesting.
Okay.
I'm interested.
Yes. So this is one way of, let's say this is one way of modeling it.
Yeah.
Yes. Yes. So this P would also reflect the intuition underlying conservatism. So next I'm going to show that the bigger the P is, the less weight people are going to assign to the sample information. So one way of looking at it, so on the left-hand side of this equation, we have the posterior mean. So it's alpha 0 plus alpha divided by eta 0 plus eta. And we can just plug in the alpha. So it will be 1 minus p times a, and then plug in what is eta, so 1 minus p plus times b times n. And next, we can express this as a weighted average of the prior mean and the sample mean. So what we do, we just take the first term, alpha 0 divided by the denominator, and then times eta 0 divided by eta 0. And here, alpha 0 divided by eta 0 would give you the prior mean. And similarly, we do it with the second term, and then here you get a divided by n, which is the sample mean. And then the weight assigned to the prior mean and the weight assigned to the sample mean will depend on what P is. And here you see the bigger P is, the less weight the sample mean will receive. So it reflects the intuition that when you have a higher probability of missing a signal, then you also place less weight to the sample information. And here, if you are Bayesian updating, then P is also equal to 0. And you are conservative when P is greater than 0. And for the situation when P is greater than 1, then it is no longer a probability. But we could still, so we can still interpret it as an extreme form of conservatism. So you can think of it as you even go back to your prior and eliminate some observations in your prior. So we call it prior signal destruction. And then when P is smaller than 0, that means you place too much weight to the sample information and too little to your prior. So we call it base rate neglect. Okay, so for both Q and P, it can capture both directions of the biases. So it's a continuum. And last, we combine these two biases into one model. The intuition is pretty simple. So decision maker, they may miss signals because of conservatism, and then they misread the signals that they have actually received, according to what the confirmatory bias would say. So if we translate this intuition into the model parameters, it basically means that we first multiply 1 minus P to all signals, all actual signals. And then, so that means, for instance, in the case when you think successes are more likely, you perceive only 1 minus P times A successes and misread Q% of the failures that you actually received. So this is the model that we consider. Next, I'm going to show you how we can make these model parameters P and Q observable from people's choices. So what we are going to do, so we are going to need estimates of alpha and beta, so which are parameters of this beta distribution that captures people's beliefs about the success rate. So then we are going to need to elicit people's beliefs. So in our experiment, we had a spinning wheel to generate as this mechanism that generates this IID binary signals. And the wheel was covered by a sticker. So the sticker has a proportion of yellow and a proportion of brown. And this was not known to the subjects. So how we decide what proportion we actually put on the wheel? So in each session of experiment, we randomly select one subject according to the subject ID that they got as the implementer. And then this implementer is going to randomly draw one color composition from a pile and then stick it on the wheel. And then later, he's going to spin the wheel and report where the wheel stopped at, what color it was, to the rest of the class. So we had no control of what type of proportion was and what type of sample information our subjects are going to get. And then we used two different methods to elicit people's beliefs. So the first method we call the matching probability method. So this method is eliciting it elicits the probability lambda that makes subjects indifferent between the following two bets. So one bet is about the wheel proportion. So we tell the subjects, you can get, let's say, a fixed amount X, 20 euros, if the wheel proportion falls in an interval, so here it's denoted by an event E, nothing otherwise. And there is another lottery which gives you the same amount of money, but with a known probability lambda, 0 otherwise. So in the experiment, we gave subjects such a choice list. So on the left-hand side, there is a list of different ambiguous lotteries. So it's all about the Brown proportion on the wheel. So for instance, if we take the fourth line of this choice list, the subject has to choose between an option which gives them 20 euros if the Brown proportion was between 0 and 12%. And on the right-hand side, they have a 25% chance of receiving 20 euros. So this is implemented through, so we have a deck of cards. There are 4 of them, and 1 of each suit, and the implementer just randomly selected one before the experiment, and then put in a sealed envelope. So subjects did not know which card was drawn, but they knew there was a card drawn, and it is one of the 4 suits. So it was very, very clear to them that it was a 25% chance. So if we move down the choice list here, we can see that on the left-hand side, this option is getting better and better. So the chance of winning is getting better, whereas on the right-hand side, it keeps the same. So in the beginning, this one is more attractive, but at some point, the subject is going to switch to preferring the left one. And then we know at the event where they switched, so if you assume, let's say, expect utility, then the subjective belief of the subject of that event would be 25%. Okay? But as I said, a moment ago, we were assuming, let's say, expected utility. So what if the subjects do not satisfy expected utility? What if he is, let's say, ambiguity averse? Then this method is likely to overestimate his beliefs.
What if the person is a probability lawyer?
Sorry?
What if the person is rank dependent?
So if you mean rank dependent in terms of risk attitude, then it does not matter because both lotteries have the risk component. So the risk attitude part will cancel.
But don't they have different probabilities?
Sorry?
Don't they have different probabilities on the left and the right?
Yes, but no matter what the probability is, the risk probability weighting function is the same. The second method that we consider is called Exchangeability Method. And what we do is we look for 2 events that are equally likely. So we give them a list. So in this case, both options are about the wheel proportion. And on the left-hand side, we let the interval increase from 0 to 100. So it's becoming more likely. On the right-hand side is the complement event of the left event. So at the point where the subject switches, they believe that at that line, for instance here, if they switch here, they would think it's equally likely for the Brown to be between 0 and 12, and 12 and 100. So we identify 2 events that have the same probabilities. And we do this for 3 different, so we find 3 different pairs, and then it will enable us to estimate the whole distribution. So in the experiment, we have subjects elicit their beliefs 3 times, and in between they received different sample information. And as I said, we don't have any control, so you see the signals that they received are really diverse across different sessions. And so I'm running a little bit out of time, so I'm going a bit faster now. So we also would like to see how the information or informativeness of the signals would affect people's beliefs. So we defined a measure, we call it the information gain. So it is measuring the distance between subjects prior and the Bayesian posterior, had they updated those signals according to the Bayesian rule. So then this captures how much the signals should have influenced the decision maker's beliefs. And later we will see this can influence the degrees of the biases a little bit. So I'm going to skip the econometric model, but the main idea is that we maximize the likelihood of observing the choices in each choice list. So to get the parameters, so we look for parameters that would maximize the likelihood of observing the choices that we observed during the experiment. So results, so I'm now splitting a very big table into several parts. So we first look at conservatism index. So in the baseline model, we found that on average, the P index is around 0.5. So it's roughly 2/3. So it's indeed people miss about 2/3 of the signals that they get. We also look at whether people's conservatism decreased in later rounds or increased. So what we found was that the pattern was not so clear, decreased a little bit in the third round, but then not so much difference in the last round. And for information gain, so here we have actually, so two terms, the information gain and information gain squared. And we see actually there is an inverse U-shaped dependence. So which means for very uninformative and very informative signals, people are less conservative. And only for the signals which are kind of open to interpretations in the middle, people are more conservative. So maybe they don't know what to do with those signals, so then they tend to ignore them even more. And finally, females are more conservative, and economics major, they are also a bit more. You may think it's counterintuitive, but they are compared to students who are following econometrics. So in a sense, those students are more sophisticated. And for confirmatory index, we have the same table. So the baseline is that on average, they misread 17% of the opposite signals as confirming. And otherwise, there is not so much dependence on other variables. So it seems to suggest that confirmatory bias, at least in our sample, seems to be a more stable trait of subjects. We also compared the two measurement methods. So for the matching probability measurement, ambiguity aversion may play a role, but for the exchangeability method, it does not play a role. So what we found was that in the matching probability, so this is the coefficient of P for matching probability, and we see that when it is compared to the exchangeability, it's significantly higher. So it suggests that maybe ambiguity aversion or non-neutral ambiguity attitudes make people even more conservative. So this is suggestive. And then for confirmatory bias, again, there is no difference. So I will skip the summary and receive some questions instead.
So now for every person, you can just measure these things.
Yes.
And then you know how to correct their reasoning and make them into perfect Bayesians.
That's the hope.
If
So.
we think favorable is normatively attractive.
But in Rotterdam, we need to agree with that, otherwise we lose our jobs. So we at least say that we agree.
So
then you have to try to elicit that from me using Carney's method.
But that does raise an interesting normative question, if I may. I mean, how would you go about using this? Let's assume that the Bayes rule is normatively attractive. How would you use this normatively to guide people to make their decisions? So it seems like you would have a metric now to evaluate
Yes.
conventions.
So I didn't think too much about it, but I think once you know, let's say that I gave this intuitive example in the beginning, you repeat the signals 3 times. So then if you really know how much, what is the tendency of people to ignore the information you provide with them, then you can try to account for that. So on average, at least people receive the information to a certain extent. So then you also need to, let's say, trade off the costs of all kinds of intervention.
I guess also another way to view this is you've got all these very interesting demographic effects. You could, in principle, do an out-of-sample test of your own theory. If women have this bias and men have it,
Yes.
That would be an interesting
Yes.
test.
Yeah, so here things are still exploratory. Then if we would like to confirm that there is really, let's say, a gender difference in terms of conservatism, then indeed an out-of-sample or a prediction test would be needed. So we need to design an experiment or whatever to target at that variable that we are interested in. Yes?
How many observations did each subject have to each problem? Was it just 2 or 3?
So in each session, each round, they get 3 more, but it's accumulative, about the same wheel. So first 3, and then another 3, another 3. So we give them a chance, let's say, to distract some of the signals from their prior as well. So in total, 9. Yes.
And your data analysis is across all subjects and across all problems.
Right.
I think people are different, so
Yes.
why don't you aggregate over everything?
So first of all, if we only look at like each individual, then the data points are very few, and we need to estimate quite many parameters. So then it's, let's say, it can be very noisy. And so I just presented a very basic model. So later we are also going to incorporate individual differences by considering a random coefficient model. So there you can say each subject has a different parameter, but those parameters form a distribution. So that will be the next step. Yes. Yes.
If I understood right, you can describe the modeling that you did as non-Bayesian learning, or you could describe it as Bayesian learning based on a misperception of what you've seen.
Yes.
So a different way to model it would have been that you do perceive everything, you just
Right.
respond to that in a non-Bayesian way.
Right. That's an alternative way of doing it.
Is that an important difference, and why did you choose your way rather than this other way?
So this other way, then how would you process the signal? So there are also many, many different ways of doing it, right? So then we found maybe this way is more tractable. So you can have, so we have, of course, quite a set of assumptions, but if you accept that our assumptions are reasonable, then you can get quite straightforward estimates of model parameters that are also easy to interpret.
Am I over-interpreting your model to say that you're saying that all of the irrationality is in the perception, none of it is in the learning?
That is indeed the big assumption that we are making here.
I think this is only interpretation that we talk about. You can just interpret it the other way, and they will have all the same numerical results. If they are missing part of the signal, or they see them all, but they don't give them enough weight, all the formulas remain the same. It's only an interpretation.
It's not identifiable, is what you're saying.
Yeah.
And I think a third option is one I was raising, that they don't start with an appropriately diffused prior. They might have I don't know what irrational prior means, but they might have a prior that's sort of degenerate in some sense.
Do they assume the same
No, we don't. So here, so in this, so in the analysis that I presented here, yes, but we are also going to extend it so that we allow for different priors for different individuals.
Then it might not be identifiable, but this point, because this P which you have over there, right, once you integrate into the and split the formula, right, so the same effect would be achieved by just increasing the alpha 0 and beta 0, so basically making the prior more narrower, right? So in a sense, these are kind of equivalent ways to one and the same thing. So then if you try to estimate alpha 0 and beta 0, you might not be able to do it.
So it's possible, but if we just eyeballing the questionnaire, then in the first stage, most of the subjects have a prior that is very close to beta 1, 1. So it's because we have this choice list, right? So then, for instance, here if you switch at 50-50, then you know the median is 50, and then 25, and then we have a choice list with 50% and 75%, and then you have a uniform prior would then say you think the median of this distribution is 50%, and then the 25% is 75%. We have also, but so you mean if it's 50%, right? Then when you bet on when it's, let's say, 75%, then you will not switch at.
There exist different priors that can explain that initial response. And I think the answer perhaps yes. I don't know. And that raises the identification problem. But you could circumnavigate that by eliciting prior beliefs.
We did. Yes, so we did. So our choices that, so the elicitation allows us to actually identify priors as well. It's just that in this set of, so in this econometric model, we hasn't taken that into account, but we can do it using our data.
Okay, I recommend we should take the rest of the discussion.
Thank you.